Okay. Hopefully everyone's got seat. Sorry for the trouble for meeting everyone. Somehow the registration software seems to have missed a few people, so we'll try to sort things out and make sure that we have food for everyone at lunch and dinner. So we'll try to make sure that everything goes well. So welcome to the European GNURadio Days 2019. Just a quick few words of introduction, just to make sure that everyone knows how I see things happening for the next few days. So just first of all, a bit of historical background. Last year, I've seen quite a few phases that are come back to this year. Last year, under the motivation of the staff of Lyon, of INSA Lyon, of Tanguy, of Léo, Mathieu, they were thinking that we were missing in Europe a dedicated conference towards GNURadio and software-defined radio, but dedicated to GNURadio. And so last year, we organized the French GNURadio Days. Now, there was a bit of a misunderstanding or a difficulty in understanding whether French related to the French language or to the location of the conference. And quite obviously, most attendees expected that it was a French language conference, except for Paul, who kindly attended. So he was the only non-French attendee to the French European conference. So this year, we made sure to make things straight, and it's now European GNURadio Days, not conference, not to compete with the GNURadio conference in the US, of course. So to give you a bit of a hint of what we would like, so you see here we have the multimedia team recording everything. For last year, it was Pip doing the work. So you might have a look at the YouTube channel where we broadcast the last year's recording. And we would like to do the same this year. Now, of course, we do this only with your authorization. So if anyone would like to prevent anything from being recorded, let us know, and of course, we'll stop recording. Also, all these recordings are not live broadcasts. They will be post-processed before broadcasting. So even if you want some recording to be edited, let us know, and we'll make sure that things that you don't want to get out of a conference don't get out. So when we defined the conference, we said we wanted a conference that bridges the gap between technical engineering and scientific and research. So basically, we see GNURadio as a framework for prototyping discrete time digital signal processing, but with a focus on application. So one participant mentioned it's a strong academic participation. And of course, most conferences are with mostly academia people, but I really would like to focus on the practical implications of the work of using GNURadio, so going from theoretical, from algorithm towards practical application. That's my computer. So what's going to happen for the next few days? So the first day today is dedicated to oral presentations. You've seen that we have 1 hour and a half sessions. We've got chairmen that will try to make sure that we stay on track. So please, speakers, try to make sure that you keep on your half-an-hour slot, including installation. For those who have not sent me their presentation, it would be most convenient for the multimedia team if you can give me on a USB stick your presentation so we can run it on the host computer rather than bringing your own computer. It's a bit easier for us to record everything for the presentations. So for those who have not come to see me, please come during the coffee break and give me your presentation USB stick. At the end of the day, we'll have Markus Müller from Karlsruhe Institute of Technology, from KIT, giving the keynote speech on GNURadio internals. I don't exactly know what he's going to talk about, and I'm looking forward to hearing his presentation. And this evening, because you've seen that Besançon is rather a smaller city, a smaller town, and it might not be obvious for everyone to find dinner, we organize a barbecue. So the barbecue will be hosted at NSEM on the lawn in front of the school. It will start around 7:30, 8. We asked for 8 p.m. The person organizing this said he would be a bit earlier. There's beer, there's wine, so please join. You can consider this as a social event. I think actually it's the most important part where you can share information with others. The hall will stay open, so you can still look at the posters, you can still look at the experiments, so try to join for the barbecue. It will be from 7 p.m. to 10 p.m. this evening, and will be the opportunity for you to share information. Buses going downtown for those who are coming by public transportation. I checked, there are buses at least until midnight, every half an hour from 10, 10:30, 11, so you're safe to go back home. So that's the first day. Again, all presentation will be recorded. If you don't want your presentation to be recorded, let us know. Second day, the tutorial will be held in the 2 computer rooms that are kindly provided by NSEM. It's 2 times 28 computers, so that's 56 computers. There's obviously quite a few more people in the room than 56, so if you are a group of people coming together, please try to share a computer during the tutorial sessions. We'll try to squeeze everyone in the rooms. I'm still not sure how we're going to do it, but we'll try to make sure that everyone fits in these 2 rooms. Because the policy of NSEM is to have only Windows-based computers, you'll see that we'll run the tutorials on VirtualBox, which has been a bit of a hassle, but we believe that everything is working well. So we'll try to make sure that everything works well. You've seen that the tutorials are based on the Pluto SDR, the board from Analog Device. Analog Device has been very generous in supporting the conference, so the team of Analog Device is with us in the room. And they have provided the Pluto SDR that you have in your bags. So I tried, because the deadline for subscription was May 1st, I tried to make sure that everyone that had subscribed before May 1st has a Pluto SDR. If that's not the case, please come and see me. We'll try to sort things out. And for those who registered after May 1st, I tried to take the spare Pluto SDR left by saying that organization staff would not get one, people who I know get one from their university will not get one, and I tried to share it amongst the people who have registered after May 1st. So if you are disappointed by your bag, please come and see me. We'll try to sort things out. So again, great thanks to Analog Device for providing all this hardware and allowing us to make the tutorials on their chip. That brings me a bit to a Pluto SDR. So that's just a quick introduction about what I've been spending the last 6-7 years just playing with the low-cost DVB-T. That was what we were using last year. And I think really this hardware is again a show changer. I mean, the DVB-T was really the low cost, and I believe that it made software-defined radio explode because it gained access. Everyone got access to software-defined radio for something like 10 euros. And now, for about 100 euro, you get the frequency span not limited to 1.6 gigahertz, but you go all the way to 6 gigahertz. So this means that you have access to a 2.4 gigahertz range. I find it absolutely fascinating that for about 100 euro now, you get about 64 megahertz bandwidth, 6 gigahertz top frequency. That's just completely amazing as hardware. And so you will see a few presentations that are not exactly GNURadio centered. I've put here this phase noise. Actually, maybe you've seen that, that there are some GNU Linux magazine outside. So Linux Magazine Diamond Edition is a sponsor of the conference. They're giving you some of the magazine. And that was one of a curve that we published for analyzing the Pluto SDR. And you will see a few presentations that are not centered on GNURadio. The laboratory hosting this conference is FEM2SC Time and Frequency. So we did try to put a bit of a focus on our knowledge, which is frequency stability and time transfer. So you'll see a few experiments outside about radar, about timing measurements. So again, there is a lot of opportunities with this low-cost hardware to do some very nice characterization. I know that Claudio and Carolina at the back of the room will be presenting topics related to phase noise. So I think phase noise is really a core issue that not so many people know about in the computer science and software-defined radio. And that's your first characteristics. I mean, remember that if you do a phase modulation, you're measuring a phase. If your local oscillator is not stable, it's going to be difficult to extract the phase information. Here in this example, that's the temperature-controlled crystal oscillator of the Pluto SDR, which is excellent at short term, but on long term it's drifting, of course, because it's a TCXO. And if you replace it, I have the experiment outside with an oven-controlled crystal oscillator. You have poor, far from carrier phase stability, but you have long-term stable signal. So I think, again, this low-cost hardware does not mean low-cost experiment. It's still the opportunity to be doing some very nice science, as will be shown by the colleagues from INRIM, from Torino, from Paris Observatory. We have one presentation, and our colleague from Fem2ST will be introducing some of our activity on phase noise and phase analysis. Just a few statistics, which apparently are completely wrong from the people I see in the room. I had expected about 85 to 95 registry. I think that quite a few more people show up, so I'll try to figure out how. Country distribution, obviously it's in France, mostly French people. I mean, 2/3 of the attendees are French. But still, I'm very pleased to see a very strong German staff. Of course, colleagues from Munich have joined. We have colleagues from Freiburg that should be joining us shortly. We've got some staff from USA joining us. We've got some colleagues from Romania, again from Analog Device, some Dutch people coming with us, Swiss, Finnish. I got some email from Indians. Are they here? There's 2 Indians that should be coming. That was very late. Italy, of course, Belgium, Spain, and Algeria. So we've got actually, it's becoming European. I think it's obviously English will be the language this year, so that's the official language. And origins of, so this actually is a bit of a pie chart that I tried to classify. I'm not really sure, like for example, Fraunhofer Institute, I don't know if I put you in government agency or if I put you in academia. So I put Fraunhofer in government, so that helps me to grow a little bit this part of the pie. So you see that actually we have mostly academia, but we do have some companies coming in. We have some government agencies. So government agencies, I put this military, I put this space agency, and I put this as development agencies that are not dedicated to research, from my understanding. And then there's others, which is ham radio, students, and the people I didn't know where to classify. Sponsors, again, Analog Device has been very generous in providing the Pluto SDR. Linux Magazine has made the advertisement. Groupement de Recherche Network Research Group has supported, as well as First TF financially. Rodenschwarz, you might think, why is an oscilloscope manufacturer sponsoring a software-defined radio conference? Rodenschwarz is going to demonstrate their hardware. I have one experiment outside, which is fetching data from a wideband oscilloscope using a from wideband oscilloscope in GNURadio. And basically, whenever you need high bandwidth, discontinuous data sets, an oscilloscope makes an excellent software-defined radio source, and I'll show you how you can use these for radar measurements. You can have centimeter resolution with a 10 gigahertz oscilloscope. You have centimeter resolution on distance measurements. So I do believe that oscilloscope, high-speed oscilloscope, are appropriate software-defined radio sources. We've got the laboratories, affiliations of the organization, and Armadillo Systems is the cause of all this work. Armadillo Systems is a company from Mulhouse. They're manufacturing boards combining CPU and FPGA before the Zinc was created, and they have sponsored a lot of this work. So thank you for Armadillo Systems, Opossum. Wednesday, I expected to extend a little bit the stay to a subset of the participants, so I'll not stay too long. I think that one of the challenges of software-defined radio is to put the line at the right place between FPGA processing of a radio frequency stream and CPU. And that's a very challenging work. I mean, we know that writing anything in FPGA takes forever, but FPGA are fast, CPU are slow, but they have higher languages, higher level of abstraction. And so we've spent, our colleague Gwenelle Goavec and Pib have spent a lot of time for the last 5 or 6 years developing a co-design framework, and we would like to promote this framework. So that's not going to happen at NSEM because you need so many software. We need Buildroot, we need Vivado, we need a working Linux computer, so we cannot do this on VirtualBox. It would be an 80 gigabyte VirtualBox that doesn't make sense. So for people attending the Wednesday tutorial, we will meet at NSEM at 8:30 and walk all the way to the university. That's 15-minute walk. Or if you want to wake up a bit later and you know where the university is, we can join at 10 to 9 at the university. That's Bâtiment Propédeutique. And so that we're at 9 a.m. in the computer room to get started with the tutorial. People ask me, when do you expect it to finish? Because we need to leave to get a train. I don't know exactly how long it's going to last. I can tell you it lasted for the last 6 or 7 years, so you can imagine that it might last a bit of time. Basically, you just leave whenever either you give up or you have to get your train. What we would like to do is to try to make it like the morning tutorial will be a step-by-step presentation of adding a mixer. Of course, mixing, well, the AD93763 is already doing the mixing, so why would you mix on the PL, on the FPGA? Well, that's just for introducing the topics, and in the afternoon, I would like you to help you show you how to decode CDMA messages, and of course, because GPS is CDMA, I can show you that you can decode GPS on board the FPGA of the Pluto SDR. I don't expect everyone to have a GPS signal after 8 hours of tutorial, but I hope that you can all go back home with the knowledge how to complete the tutorial of turning your Pluto SDR into a GPS receiver. To be completely true, that's the acquisition phase of GPS. I don't know how to do tracking yet. So I expect to finish at around 5 p.m. And finally, because I should stay on time, I was wondering, what about sightseeing? Where can I send you? I don't really know what's around Besançon. And then tonight I figured out, yeah, maybe there's one place that this community would like to visit. You might know that in France we have a radar dedicated to space surveillance, GRAV, which is, I've forgotten. GRAV is the radar system for detecting satellites flying over French territory. And GRAV is actually a Grand Réseau Adapté à la Veille Spatiale. So that's the large network dedicated. No, actually, I wonder why it is adapted to space surveillance. And actually, GRAV, the emitter is a bistatic radar with the emitter actually 50 kilometers from Besançon, and the receiver on Plateau d'Albion, south of France. So actually, it's a bistatic receiver using the whole of France as the distance between emitter and receiver. And actually, you can go there. There's a large fence. You can see through that fence. I don't really know what you can detect out from watching. And there is a big board, no picture. So, of course, I didn't put any picture of GRAV radar. But the nice thing about leaving 50 kilometers from a 500 kilowatt radar is that you just stick a wire out of a window and you've got the Doppler shift of all the planes flying in the area around Besançon. So if you have a car and you want to visit, GRAV is just 50 kilometers northwest. There's hardly any surveillance. You can visit it. I would not advise taking a picture, but it's one place that you can visit around Besançon. So that's pretty much the introduction that I wanted to. I should not speak much longer. Any question, any comment? Any uncertainty about your stay here? Everything's good? So with that, for the speakers, please use the microphone, not so much because you might not be heard, but because, again, sound is recorded. So if you use the microphone, you make sure that you have good sound quality on the record that will be broadcast after the conference. So if there is no question, no comment, I would like to get started with the first session. So the first presentation So the first presentation is dedicated to array signal processing optimization in GNURadio for tracking and receiving applications between ESL and French XLIM. So, Clément.
Good morning, everyone. Thank you for hearing me today. Thanks for this introduction as well. So my name is Clément Campeau. I'm a PhD student working for the French-German Research Institute of Saint-Louis, or ISL, and the XLIM laboratory at the University of Poitiers. And today I'd like to present you some feedback on the work some of my colleagues who are present here today and I carried out. And that consists in modifications we brought to our GNURadio projectile tracking application. So I'll try to focus on practical aspects more than academic ones. During this presentation, I'll start by telling you a bit more about the context that motivated this work and how we ran into the need to change what we had already done in GNURadio. And then I'll detail some of them. I'll start with our questioning of the hardware setup we've been using so far, such as the maximum data throughput we could exchange between our USRPs and our master laptop, or the recording speed we had at our disposal to for our measurements. Then I'll tell you some details we changed in our software implementation before I conclude by explaining you a bit about a very specific need that we had due to our application. So first, as I mentioned, I'm part of the ISL, where we, with our team, we work, among other things, on projectile instrumentation and the implementation of secured communications between ground station and these projectile that we instrument. To do so, we've been using antenna arrays for a very long time. Indeed, they offer many advantages, among which the directive radiation patterns that can be dynamically reconfigured. So for those of you who are not familiar, here's a small animation of an antenna array made of a few antenna elements that's working in transmission mode. So of course, reception mode is the same reasoning. We'll be seeing that later. And in this case, you can see that all radiating elements are radiating the same signal, and the global wavefront is propagating perpendicular to the antenna array axis. But if you introduce some phase shift between your antenna element signals, then you can tilt that wavefront by a certain angle that you can control depending on that phase shift. And that's a very important property, as we will see later. That's what we're going to use. So for our specific application, we've been using a 4-element linear array that was designed at the ISL for 2.3 gigahertz applications. And in this application, we're willing to steer that antenna array using our USRPs and some GNURadio blocks that we design here. And our goal is to perform projectile tracking. That is to detect the direction of the signal that is transmitted by a flying projectile and to favor reception in that particular direction at all times. So if you take the antenna array that I showed you just before and if you put it right at the median to the projectile trajectory, then our goal is to always favor radiation towards the flying projectile. Here's shown to you a quick schematic of our experimental setup. You can see that our USRPs are connected to the array and are controlled by our master laptop. And all stuff is gathered into a bunker for security procedures. So we had to use a remote trigger with a barrier correction line. We'll see that later, how it influenced on our experimental setup. So here you can see a quick picture of that true setup, and our system proved able to follow a projectile flying at Mach 1 and above and record data at the same time. So far so good, you may think. However, that was true when we ran our program at a 1 megasample per second sampling rate. Problem was when we tried to decode telemetry data with a transmitter functioning at 2 megabits per second, that was too slow. So obviously we had to raise our sampling rate, and when we tried to do that, we encountered overflows. That is periodic losses of data, as you can see here, for a few seconds. And to give you an idea, our projectile flight is approximately 1 second long, so if an overflow occurs at that specific moment, then we get no data. That's something we could not put up with, so obviously we had a need for the optimization of our program so that it would be able to run at our objective 8 megasamples per second. Well, that brings us to questioning what we had so far. So first thing was, are we sure that our hardware setup will be able to handle the increased data throughput? So here you can see what we had been using in the first place, a simple Ethernet switch, and there's only one Ethernet cable, 1 gigabit, that was linked to the laptop. So if you make quick math, you will quickly conclude that's not going to be enough when you increase that sampling rate. So we decided to move on to a Thunderbolt 3 interface. And here, with 40 gigabit per second maximum of data throughput for the Thunderbolt, the limiting factor will be the Ethernet cables going from the USRPs, but in our case, that's going to be enough. So that's the setup we used for the rest of our experiment. Second point was that we were willing to be sure we could record our samples fast enough. So our laptop was equipped with a Samsung SSD that can write at a 520 megabytes per second as a maximum announced by its constructor. And we decided to add some DDR4 RAM that could write approximately at 21 gigabytes per second instead. So by implementing the RAM disk, we could go 40 times faster approximately than the SSD. So that's what we've been using in the following. Now that we're sure that our setup is not going to be the bottleneck for our application, that brings us to questioning the blocks that we have been implementing so far and try to rethink them, not only this time in terms of ease of implementation, but also in terms of performance. So the first thing was the data format we recorded. The native GNURadio complex that are available are twice 32-bit data samples. But if you look into the USRP X310 that we were using, their converters and over-the-wire samples, we realized that was twice 16 bits. So obviously the rest of it are just waste of space and time when you record them. And we had to rather convert them back to twice 16 bits before we record them on our RAM disk. So here's just to show you the difference between the use of GNURadio native blocks we had in the first place and then blocks to convert them back we used for the following. Once that was done, we decided to affect one or several of our processor cores to our most resource-consuming algorithms to make sure, excuse me, to make sure there would always be a thread available at all times when we needed to process their work function. So here you can see that for two of our blocks, we've been affecting one dedicated processor core that was only used for this algorithm, while the remaining of our less consuming functions had to share the remaining pool of our processor cores. Next point is the use of vector-optimized library of kernels, also known as VOLC. So that's a library of kernels using the single instruction multiple data capabilities of the processor. So that's very good when you want to process a large amount of data with the same processing function. That's really nice because that's exactly what we are trying to do. So we took the bet of using VOLC as often as possible after we compared this very block with these two processing ways. And in our case, it appeared that using VOLC saved us around 30% execution time. So if we look at how we did that, you can see that this simple implementation for our block with VOLC, only consisting in calling two VOLC functions. And if you compare that with how it was done with the native sample loops inside GNURadio, we see that that's really not a big deal in terms of implementation, so we are willing to do that to save that much amount of time. Now we're focusing on improving how we communicated information between our different blocks. So if you think about that, of course, the first thing that pops to mind will be the GNURadio native tags. So as a reminder, it is metadata information that is transmitted from one block to the others within the data stream. So one tag is associated to one or several samples inside the data stream, and it will be seen by the receiver block at the same time it will see the data stream itself. and it's a one-to-one isosynchronous communication means, as it was detailed and described in the GNURadio documentation. Second way, as a native, would be messages. So this time, the information is transmitted to other blocks separated from the data stream. It will not be handled inside the block function, but in the subscriber outside, in a message queue that is managed by the GNURadio scheduler, and it's defined as a one-to-n asynchronous communication means. And finally, I will present you quickly what we did with shared variables. We decided to add this way of communicating to us GNURadio software and the ISL. And if we had to present it quickly, we would define it as the end-to-end asynchronous communication means that has to be used the following. So first, the user requests a shared variable pointer as for its variable ID. So you can see here an example when we're requesting a variable named DOA. And then we give the developer access to setters and getters, as you can see with write and read operation examples, to manage this shared variable value when it's needed. And if we had to give pros and cons on this way, we would say, as I told you, to end-to-end communication means that once it's implemented in an out-of-tree module, you can use shared variables in other out-of-tree modules by simply adding a line to your CMake list text file. We would also say that receiver blocks can read the shared variable whenever they will need to inside of their work function execution, so that can be controlled by the developer instead of being handled in the scheduler as with the messages, for instance. And that each block can update that shared variable at all times during its own work execution, so that will be instantaneously seen when other blocks start their own work function. And finally, it's thread safe. The first drawbacks that we could think of now is that there's no synchronizing or priority mechanism yet. So for concurrent write operation, that means that the last block to write a new value basically wins. And that there's no explicit link shown in the flow graph for this communication means. So if you're not accustomed to using them, that could make your flow graph a bit less readable. But as you can use these shared variable IDs as a string parameter of your block, you could always see which blocks are using these shared variables to communicate. And finally, I'll quickly tell you a bit about what I said was a remote trigger. As you can see here, we were not physically present in front of our laptop during measurement, so that's another constraint from our application. And to perform that remote trigger, we use this simple orange box you can see here to send a low-level pulse of around 10 milliseconds large on our coaxial line and received on the USB port. During our security procedures, we had a 10-second countdown before the firing. We were starting the recording of our samples 3 seconds before the firing and up until after 3 seconds for, if you remember, a flight that is approximately 1 second. And to use that remote trigger that has to start after the run of your program, if you think about GNURadio native blocks, the first thing we could think of was using the burst tagger blocks and propagating that trigger with the data stream as it's shown here. But that's something that really bugged us because when you're willing to increase the sampling rate just as we did, then you're just using a increasing resource-consuming way of propagating that trigger. So that's something we would definitely want to remove from our application. So I showed you the native way. So if I just use the data format I was telling you about a bit earlier, you will see that's not really changing our problem. And we were willing to avoid that at 8 megasample per second data stream. So our first idea was, okay, we went through the trouble of implementing shared variables, so let's use them. And here you can see that we used the shared variable we named trigger to do so. And we separated our trigger as a software data stream that we controlled with a throttle block at 1 kilo sample so that we would be sure not to miss the low-level pulse when it came. And we were at first very happy about ourselves because that made our program work without overflows in static configuration in our laboratory. But what we had definitely not seen coming was that additional 6-second delay that introduced between the moment we pushed our button and the moment it actually started recording samples into our files. So obviously that was not the good way of thinking, and we changed our minds. So far we are still not absolutely sure about why it introduced that huge delay. So if some of you are more comfortable, we would be more than happy to discuss that later. And then we went back to using the native messages in GNURadio for that trigger. And that allowed us to record our twice 16-bit samples with only a 1 megasecond delay after our trigger. So that's the thing we used. To quickly conclude, here's a small figure of what we got after we performed our measurement. So that's a measurement of the estimated angle between our antenna array and the projectile during its flight. And that showed us that we were on the good way. So you can see here that for 6 different shots, we have something quite reproducible between them. And that's still close to what we expected in the first place with a simple theoretical model. So that's just to summarize. We brought several modifications to our application so that we would be able to run it at 8 megasample per second on each channel. And to do so, we first made sure that our hardware setup would be able to handle the increased data throughput. We changed the data format and implementing a RAM disk to optimize the recording of our samples. We also allocated dedicated processor cores to our most computationally heavy algorithms to make sure there would always be a thread safe when they needed to execute. We used Volk as much as we could to save time during processing and reduce the number of streams between our blocks, even though that could seem tempting at first because of its ease of implementation. Finally, we also used and implemented a thread-safe shared variable communication means that could fit some very specific needs for some applications. And finally, we adapted our remote trigger so that it would fit the particular needs related to security procedures when we're firing projectiles. And with all these changes, we finally managed to run our application at 8 megasamples per second without any overflows. So that's what we wanted to share with you today. I really thank you all for your kind attention. I will do my best to answer questions if there are. And if you have some things you could advise us with on some things we haven't implemented yet or that could be improved, we would be really happy to share about that later. Thank you all.
So we've plenty of time for a few questions. So do you have any questions about Clément's work? Is there another mic to pass to the audience, or is this the only one? Oh yeah, okay. Okay.
Questions?
People are really shy. It's the beginning in the morning. Oh, there's a question. Okay.
I have one question regarding the USRPs. Did you sync them somehow, like the oscillators, or not at all?
Yes. Yes, we used two USRPs that we synchronized using an octoclock with PPS and 10 megahertz reference, and that octoclock was fed using a GPS signal.
Okay, thanks.
Thank you.
Hi. I have a small question, which is, you said that you can't be near your computer while you are starting the measurement, and you use a coaxial line to bring the trigger, but why not use just the Ethernet line between the Etus and your computer and keep your computer in the bunker?
Indeed, that's something we would really like to do. Our problem with this is that the coaxial line was already buried inside, so that's something that's available. We are not the only ones doing our measurements at that time. You can imagine firing projectiles takes a lot of staff. We have people specialized in pyrotechnics, for instance, ballistics, and we are sharing equipment with them. And vehicles are also, people also drive vehicles in between, so if you don't bury your line, you're facing the risk to damage.
I'm not familiar with your work, but do you already steer the transmission towards the projectile?
I think for this specific application that we showed here, the transmitter was omnidirectional. We have been performing directive transmissions on projectiles in previous studies. I think for this one, that was not the case.
But then is there a closed loop eventually?
I'm sorry?
Will you be eventually using a closed loop, like using some Kalman filter type thing?
That would have to be discussed. So far, we are not doing it. For these specific ones, I would not be able to tell you if they're planning to do it on a short-term or long-term plan.
Thank you.
Still time for one question. Okay. So let's go for the second presentation. So we've got people from Greece and Crete. Okay, so let's start with Europe. So normally your presentation should be on. No, that's the second one. Yep, SatNogs. I'm disappointed. He just told me that he came from Grenoble. Okay, SatNogs. So it's a network, an open.
It's a network of a ground station that it's built by enthusiasts. It's a community of a ground station. So first, hello everyone. My name is Julien Nicolas. I am a contributor of this project, and I am a volunteer on this project. So it's only for fun, and also to build something that is useful to people, and but there is no money involved at all. So first, in the sky today there is a lot of objects all around Earth, more and more objects. There is geostationary satellites, and also all other satellites that are moving from our point of view on Earth. And for example, the LEO orbit, where there is a lot of satellite today, the CubeSat satellite, for example, are moving from the point of view of Earth. So to be able to get data from them, we need tracking. And because they are in line of sight in a very short amount of time, it makes sense to build a network of ground stations, because you need to share the antenna time of your ground station, because the satellite will be in line of sight during maybe 10 minutes or less. So this project is about this, building a ground station network in which everyone can add his own ground station. So today the network looks like this. It's a view of the network. The satellites pass in the sky, and the ground station track it and record the data. The coverage of the network is quite wide, so we can sometimes even track from 2 different ground stations the same satellite. It enables us to do continuous tracking sometimes. So here you can see the green line is the satellite path in the sky, and the green dot is the ground station, and the purple or the orange line is the data connection between the satellite and the ground station. And the color is depending on the frequency. This is a map that is made real time in a 3D. It's a 3D view. It's a 3D real-time view of the network activity. But it's only a screenshot for here. But I can show you it real time if you want. So how does it work? It's really easy. There is a global network management that the network, the user asks the network to do an observation, and all the ground station ask the network what the jobs are needed, and then the ground station do the tracking of the satellite, save the observation, and send it back to the network. And then the user can fetch the observation on the network. So today the network is like this, green dot are ground station. So the coverage is quite wide. So it works with 3 different parts, the ground station itself, the network, and the database. First, the network. It's a web application made in Python, where the user can ask for an observation and also get the data from an observation. Then there is a ground station itself that is made with a small single board computer, like a Raspberry Pi, and of course a SDR receiver and an antenna, and sometimes 2 or more different antennas to be able to do receiving in different bands. On the small single board computer, there is a GNURadio that does the data processing. On the other hand, the database holds all the data from the observation and also all the transponder data, because it's very important to have a database with all the frequency and the modulation of every satellite. And we also have a data warehouse, and we can do a graphical analysis of the data, of the observation data. From the point of view of the ground station owner, when you want to schedule an observation, you have all the past prediction in the sky above your station from the next 3D, and you only have to click schedule, and it will program the observation in the next 3 days or so. So you have the path in the sky, you have the name of the satellite, if the previous observation were successful or not. It's the little green bar or red bar. You have the path of the satellite in the sky, and you can also see if there is an observation that are overlapping your previously programmed observation. And then, if you are, for example, a satellite owner, you can also schedule observation on the wide network in one time. Basically, you only have to give your satellite name, what transmitter you want to listen, and the time window, and it will give you all the ground stations that will be in line of sight of the satellite during this amount of time. So you can have the bar which corresponds to the line of sight of the ground station during the time of the ground station, and you can see that there is overlapping of the observation, which is very interesting because we will not lose out all data. And when you click schedule, it will create the job on every ground station of the network. So the ground station is made with a Raspberry Pi, an SDR, You can also use higher-end SDR, for example, USRP. You will also need an antenna. On our website, we provide open source design of different antennas that are well designed for this purpose. We also provide a rotator design, which we can have a look in the entrance. And also, if you want, you can also use omnidirectional antenna, and so you don't need an antenna rotator. Everything is on the wiki. So when it's finished, it looks like this: small computer, power over Ethernet, and also an LNA and the SDR, which is here. So it's a quick example of the design, the mechanical design of the rotator, that you can find it on the wiki. To build it, you only need a 3D printer. So it's an example to show how it's well documented. When it's finished, it looks like this, with also an open design antenna. But you can also use commercial gears. So it's fully compatible with commercial gears, antenna rotator from Wimope, for example. So now, the signal processing that occurs on board. So all the signal processing run on the small Linux computer, the Raspberry Pi. So there is not a lot of horsepower available to run the flow graph. So we need to have a few tricks to be able to do it. We have one GNURadio flow for each modulation. Today we are able to decode quite a lot of different modulation, but it's near always the same. We also are able to demodulate the weather picture from the NOAA satellite. So like in every GNURadio flow chart, it's near always the same. We first do the raw data acquisition from the hardware. So we use Osmo SDR, but we are currently developing the SWAPI driver to replace it and to be able to use near any SWAPI peripheral out of the box. So today, this out of tree module is usable. You can use it. It works very well, but it's not fully implemented in our network. We are currently testing it. Then we do the resampling to be able to run everything on this small single board computer, and it still sometimes crash. And then we do the Doppler correction. So for this, we have a custom block that in our out of tree modules. After that, we do the demodulation. So it's vary on the GNURadio flow graph that it's being run. For example, there is a little more than demodulation sometimes when, for example, for the weather picture decoding. We also do the waterfall generation in this GNURadio flow graph. It's a custom block that writes a data file, and then we process this file with a matplotlib script. We do also the IQ dump, but we don't do it on every observation because of the size of it, and also to the where because it will destroy the SD card of the Raspberry Pi quickly. We only do an audio dump of the raw data because it's very useful because we have a lot of tools that enable us to process this intermediate frequency that is written inside the audio file. And also we write the data output file with all the decoded data. Donc for example, in AX25, we will see the raw packets. So for example, the Morse decoder look like this. We have the data acquisition here. Here, the Doppler correction that is made with the input that are from our script that generate a RigCTRL message. Then there is filtering and processing of the data. So it looks like every time the same. So on the ground station point of view, you can also use it in a standalone way. This enables you to do your own observation without sending anything to the network. So basically, what is it? Is that you can run any GNURadio flow graph with a Doppler correction, and you only have to provide the TLE, which is the orbital parameters of the satellites you want to observe, and the flow graph, and when you have to run it, and it will run it automatically and do the Doppler compensation. So these things can be totally used, for example, for radio astronomy, for example, or anything else. That's the first purpose of it. There is also, when you are in standalone mode, a way to send command to satellite that is suitable only for a satellite team, for example. It uses only GNURadio, and it enables you to send telecommand to a satellite. And it was used with success with the UpSat satellite 2 years ago. And this is also fully open source. So if you are building a CubeSat, you can totally have a look on it, on how it works, and use it in your project. A typical observation looks like this. You have the name of the satellite, the name of the station, and a way to say if the observation is good or not. And you have the waterfall on the right. You can see the data that is successfully Doppler corrected in the center, right and really straight. And there is 2 other signals that are from another orbit, or maybe from the Earth, that are wrongly Doppler corrected. So you can know that it's not the satellite you want to receive. An example of the data you have in the observation. So there is a data table, and inside there is all the raw content of the packets. Also, you can download the audio file of this recording, for example, to be able to do processing later on it. Another example of a more special observation, it's a weather satellite picture. So the waterfall looks like this, and then it automatically decodes the data, and you have a picture. This one is not perfect, but it's a picture. Also, something very important at the end of the project is to do something with all the data we decode from all these packets, because a lot of telemetry packets have very useful information in it. So we aggregate all the data to be able to make a real-time telemetry display, and it's useful also for satellite teams. And we can even send alert email with this. You only have to give a criteria on to make an alert. For example, this is it's totally real time, and it's network wide, so it's Earth wide observation. Like I said previously, the big problem with satellite is that all the information about frequency and modulation is not in a central place. It's everywhere on the internet, on the satellite website project, and sometimes it's very hard to find. So we built a database with all this information, and this database is totally open to contributors, and it's very important that everybody can contribute to it. So we have something very complete. The network is very wide today. We started in 2014, so it's quite old today. There is more and more ground stations on the network, every day there is about two new ground stations on the network. So now, to come back to the GNURadio, we have several out-of-tree GNURadio modules. The first is a SatNox out-of-tree module, which are the custom blocks used for the project. So it's enable you to do the Doppler correction and a few other useful things. We also have the GNURadio SWAPI module. So you can use any SWAPI device in your GNURadio flow graph. It's also useful to be able to use a remote peripheral on your network, and it works very well. We also have a GNURadio module for LEO. It's a space channel simulator which enable you to do simulation of the transmission between Earth and an object in the LEO orbit. We also have a CCSDS implementation, which is a recommendation for telemetry and telecommand protocol. So basically, if you are building a satellite, you should take a look to this because you can implement a way to send telemetry and telecommand in a very open way and in something that will be very useful in the long term in your project. To start to have something that is a bit unified. So you can join us and build a ground station. You can also contribute to the community. You are also welcome to use all these GNURadio out-of-tree modules and to contribute to them. So thank you. If you have any question.
Okay, we are ready for your questions. I may start with a question. You're a ham radio guy? Yes. So how many people are from this community in here? Well, okay. It's a very, very interesting community that is really used to share their knowledge with other people. And that's, you find a lot of people working with GNURadio in the ham radio community, so it's quite interesting. Yeah. And
there is something special to mention about this. Is the new geostationary satellite that we have is a very nice playground for SDR because we have uplink in the 2.4 gig band and downlink in 10 gigs, and it's the perfect use case, for example, for a Pluto SDR to do the uplink and the downlink. And there is a lot of things to try, but of course, get the license first.
Thank you. I would like to ask a question. So I think that this is very interesting also for radio astronomy. And one thing that would be very interesting for radio astronomy, especially if we take inspiration on the new results of the black hole picture and everything, would be to have a sort of a phase synchronized set of receivers that you could use them together to, I don't know, to observe things in the sky and to make measurements. Would that be feasible, or is that possible? Have you ever thought about this?
Yes. So for this, the problem is to be phase synchronized over a wide area. It's quite impossible. Because the best way to do it is to have common signals that you receive and you lock on the phase of these signals. So, for example, a TV transmitter or anything like this. But for something very wide, I think it's very hard. And also about the radio astronomy part of this, today in our network, we always do the Doppler compensation. So it's a big problem for this. But we also have the need to be able to find which satellites have which TLE. Because when there is a launch, often there is a TLE lottery. So we want to be able that the network will be recording all the data, and by the analysis of this data, we will be able to find which TLE are which is objects. And it's something that will be very useful for all the community. Today, we do this by hand.
Hello. If I understood well, the processing of the data is done on board, on the Raspberry Pi, on the ground station.
Yes.
So only one user can use one ground station at a time. Is that a crazy idea to do the processing on the client side instead of in the ground station?
On the server side?
On the server side, yes. So that
it will be interesting to only have the raw data that are going on the network. The problem is that in a lot of parts of the world, internet connection is not cheap. And you want to really send the smallest amount. For example, if I go in the network, if you to see that, for example, we have a ground station in Smile Island. It's not an error. Huh? So here, it's quite, internet is not cheap, for example. Also in Kazakhstan, internet is not cheap. For example, in South Africa, internet is not cheap. So the problem is here.
Just a remark. I'm using the satellite station in France, okay? And I tried to put another one in South America, in French Guiana. And it's exactly what you said. Internet is not cheap. And finally, it was not possible. And I think for satellites, the problem, not the problem, but the future, is to extend satellites to Africa and South America. It's a really big problem to extend the coverage to a permanent coverage of the satellite. You know? So it's very interesting, but we need to make some efforts to work.
Yes, totally. In fact, in this area, the best is to have an association. For example, Hackerspace will have enough money and people to run it correctly. I think it's the only way to do it.
But we have to find people.
Yes.
To host the station in this place.
Yes. We are working on this.
Yeah, I will give you the mic right before. Actually, there was a second question hidden in my first question.
Okay.
I work in the IoT, on the IoT market, and actually I see a good application for such a system for IoT instead of satellite
Yes.
Data acquisition. Is that a project that you have thought about, or is this already an application?
Yes, it will be something to do, because an SDR on in lot of places in the world with a small computer and with internet, you can do almost anything. So it would be a great idea. For example, for LoRa application to have a gateway to the internet, and there is also a few open source projects to build network of this kind of thing. So maybe we can try to share our hardware with them. It could be a good idea.
Yes, thank you for this nice presentation and also for this wonderful project. Regarding this problem of internet access, wouldn't it be possible to transmit the data using radio amateur uplink to broadcast the information instead of using the internet?
Yes, it will be a good idea, but it's quite hard to transmit data which are not your data when you are amateur radio. I think that it will depend on the country, but it's really true that, for example, if you use the geostationary satellite to do the data aggregation to get all the data at the same place with only a dish and a Pluto SDR that will send the data this way, it would be great, but I think it's a bit out of the scope of the amateur radio. I think there will be problem, but maybe it's something that we can start to try to find, but it's not easy.
I would actually second the idea of phase synchronized receivers throughout the world. In my case, I would be really interested in all the web SDR, very low frequency signals direction finding. But I'm sure Paul will have more to tell us about phase synchronization of multiple receivers. So that would be really exciting.
Yes, I think that the KiwiSDR has something to say about this.
Are there any more questions? Well, it's about time to go to have the coffee break, but before that...
So 20-minute coffee break. Try to get back to the room at 40...
Okay, welcome to the FPGA SOC Embedded Signal Processing in a Platform session. And let me introduce you Adrian Sucio from Analog Devices Incorporation. And I will present the measurements on using GNURadio to do signal acquisition and analysis with Scopy.
Thanks. So my name is Adrian. I've been working with Analog Devices for the past 4 years. My presentation will be on how to do signal acquisition and analysis and with Scopy and how we use GNURadio to do that. Before we begin, I'd like to talk a little bit about Analog Devices Active Learning Program. So this program aims to inspire students understand real-world analog signals, and it tries to bring technology to the classroom. So besides free courseware, labs, books, tutorials, we also have a few entry-level hardware platforms. So there's the EDALM 1000, which is a software-defined measurement platform. We have the EDALM 2000, the board we're going to talk about today, and also the EDALM Pluto, which I know you know, which is an SDR. So the EDALM 2000, or just short, it's the M2K, is a USB-powered multifunction instrument. It is based on the same infrastructure as the Pluto, and it has a Zinc SoC that is running embedded Linux, but the analog front end is different, and it has an AD9963 chip. Also, like the Pluto, it has several connectivity options. It makes use of the USB OTG, the USB cable to connect to the PC, or you can use the OTG capabilities along with the Linux drivers that are, part of the system to connect a memory stick, a Wi-Fi dongle, an Ethernet dongle. So you have multiple connectivity options with the M2K. So the specs of the board are a 2-channel 100 megasamples per second ADC, 2-channel 150 megasamples per second DAC, positive and negative plus minus 5 volt power supply, and 16 digital input-output channels that are capable of buffered operation at 100 megasamples per second. The hardware and firmware is open source, and you can find it and hack it at the links in the presentation. So the software that we developed for the M2K is a touch-friendly, kind of modern-looking Qt-based application. It is cross-platform and runs on Windows, Linux, and Mac OS, and it has several virtual instruments that we implemented. So there's the oscilloscope. There's the signal generator, the voltmeter, the power supply, the spectrum analyzer, the network analyzer, the logic analyzer, and the pattern generator. And most of the signal processing and acquisition on the analog part of it is done using GNURadio. This software is also open source, and you can clone it. Maybe you can help us with it, and the link is in the presentation. So I prepared a small demo, like a teaching demo on how R2R ladder DAC works. So here we have, I have this circuit built here on a breadboard, and it kind of shows a little bit about the digital and analog capabilities of this instrument. So here we have the R2R ladder DAC, which is connected to the digital side of things, and I feed it digital signal from the pattern generator, and then I measure the signal here, the analog signal here, and see how it looks. And this is the application. So right now this is the signal that, the digital signal that we feed it in. It's a binary counter signal at 1 megahertz. And if we look at the oscilloscope, you can see that the output does not look that well. It kind of, we have like small artifacts here. And this is because when we did the setup, we didn't really pay attention to what the op-amp data sheet said. And we didn't power it properly. But if we go to the power supply and we set in more negative voltage so it doesn't clip the lower rail, you can see that the signal looks nice. So it is just a simple example of how you can use the ADAM 2000 as a teaching instrument for students or people who are new to analog electronics. So why did we choose GNURadio? It provides a lot of signal processing blocks that were useful for our application. The library is geared towards performance, so it should run on most PC hosts. We want to run it on Raspberry Pi. We also want to run it maybe in the future on Android-based platforms. And it also, a big deal for us was that it already had QWT-based visualization blocks, so we could hack those and we could change those to better fit our application. So in order to better understand how this system works, we should take a look at the analog signal chain. The M2K is an embedded Linux host which uses the IAO subsystem. IAO stands for Industrial Input-Output. It uses the IAO subsystem to manage its inputs and outputs. The libiao abstracts this, is a system library, and it abstracts these low-level details of the subsystem. IOD is IOD, which is IO daemon, is an application that runs on the M2K board, which provides remote connectivity to the board via USB, IP, or even a serial link. On the other hand, we use again IAO and libiao, but along with this, we use the GRIAO out-of-tree module to communicate with libiao, and eventually we use GNURadio and QWT to plot the signals into scoping. So how do we use GNURadio? We created this IO manager class, which is basically a multiplexer between the input-output of the hardware and the instruments. So, for example, you can't have instruments that use the same resources running at the same time. So, for example, you have the oscilloscope, which uses the ADC, and the spectrum analyzer also uses the ADC, but the settings between them might be conflicting, so you can only run one of them at one time. So we created this IO manager class that handles this. And this is like a simplification of what the IO class looks like. But as you can see, we kind of abuse the copy blocks. So in order to have this multiplexation behavior, we kind of abuse the copy blocks to turn on and turn off certain parts of the application, so we don't get glitches on other instruments. Even so, sometimes this approach does not work entirely, and what we noticed is that GNURadio does not handle flow reconfiguration, especially runtime flow reconfiguration that well. So in order to help with this IO manager class basically saves all the created data paths, all the created paths in the flow, and if we have to destroy, let's say, this block here, the IO manager just kind of remembers everything that is in front of that block and recursively deletes everything at runtime. So I'm going to talk about the instruments a little bit. The oscilloscope, like I said, is a 2-channel 100 megasamples per second ADC, which has a plus minus 20 volt input range and is capable of triggered operation. So some of the features that we have that we have that use GNURadio are the autoset feature, the AC coupling, reference channels, and math channels. A few words about acquisition and triggering. So in order to have, so the M2K precisely controls the trigger position. We know exactly at which timestamp the triggering occurs, and the M2K has a trigger logic core to handle this operation. However, GNURadio does not handle the concept of triggering that well, and we used, inside the GNURadio, we used string tags, which basically say the GNURadio calls the I/O buffer refill, which gets data from the M2K, and whenever this operation occurs, it also puts in a stream tag. So having the information from the trigger logic core, as well as having the buffer start tag, we can precisely draw the triggered waveform on the screen, and you can see exactly at which sample the trigger occurred. The autoset feature is kind of a user-friendly feature for people who are not that accustomed to an analog oscilloscope, So what it does for you is help you set the time base, the volt per division, and trigger settings to if you don't know how to handle all the knobs. And it uses the GNURadio FFT block to find the highest amplitude node tone of the signal. And when a suitable tone is found, it sets the time base based on the frequency of the tone. Once the tone is found, it looks at the raw data and it analyzes the positive and negative peaks in order to set the volts per division and trigger settings. AC coupling is also a feature that we have. So we don't have physical AC coupling, we have digital AC coupling, and what this means is that we have a digital low-pass filter that we implemented in order to get the signal that we want to filter out, and we subtract the two signals in order to get the filter result. However, there's a limitation as opposed to physical AC coupling. The original signal needs to be within the hardware input range. Also, another feature that we have is the reference waveform to implement this. So what the reference waveform feature does is that it allows you to save waveforms and later reload the waveform. So, for example, if you have a waveform that you know is perfect and you're analyzing a circuit and you're trying to reproduce it, you can load it up on the plot and then see how the actual waveform looks like compared to the reference waveform. And in order to do this, we abuse the vector sync and the vector source blocks a little bit. We got the data from the hardware, and we encoded it in a read-friendly CSV format. And eventually, when we want to plot it on the screen, we use the vector source we decode the data from the CSV format, and we use the vector source to display it back on the screen. The math channels are also a pretty interesting part of the oscilloscope. It uses the IO math block from our GNURadio out of 3 module. And what it basically does, it allows our software to compute the result of a mathematical equation from a string, and everything is done at runtime. So it was implemented using a Flex and Bison parser, which creates a GNURadio hierarchical block dynamically, and it can take the acquired signal as an input, or it can even take multiple inputs if you want to do functions of multiple inputs. So I have a small example here on how the IO math block works. So in this example, we compute sine of x plus sine of 3 times x, and then everything is divided by 3. So in order to do this, the IO math block parses the string, and it creates this sine block, computes it. Then it takes the x, it multiplies it by 3 here, then applies a sign on top of that, and then everything gets divided by this constant source by 3, and eventually everything gets added up together, and we get the signal that we want at runtime based on a string. So this can also be useful again for teaching purposes. Okay. The next instrument that we have is the signal generator, also called the arbitrary waveform generator. It can be used to generate basic signal types such as a sine wave, triangular wave, square wave, sawtooth, and it is all provided by the SIG source block from GNURadio. It also supports file input, so you can load in binary data, wave files, CSV files, as well as math formats from MATLAB. The cool thing about this is that it can also generate signals from math functions using the IO math block I mentioned before. And on top of this, on top of any of these signals, you can add noise if you want to have like a noisy source signal to see how your circuit behaves in, let's say, noisy environments. The next slide is a spectrum analyzer. This instrument is pretty straightforward. It uses the FFT block to compute the spectrum. We have a bunch of windows that we can apply on top of the signal, and it has averaging and marker functionality. This next instrument that also uses GNURadio is the network analyzer. This network analyzer computes the frequency and phase response of a circuit. So in order to do this, it sweeps through the frequencies that the user selected using the arbitrary waveform generator, and for each frequency, it computes the frequency and phase response, and it plots it on the screen. So this has countless applications. Also, we have Bode, Nyquist, and Nichols plot. So this has countless applications, and we actually have a new update on the network analyzer, and it has a few more features I can show off later if you want. This is the flow graph that we used for the network analyzer. I'm not going to go too much into detail about this, but just wanted to show you that GNURadio helped us a lot to implement this instrument. The logic instruments are not really GNURadio related, but I might as well mention them here. So the logic instruments support the 16-channel digital channels, which have a buffered operation, like I said, at 100 megasamples per second. So we implemented the logic analyzer and the pattern generator. We used, for plotting, we used PulseView. For signal acquisition, we used libIO and libsigrok. And for decoding, we use libsigrok and libsigrok decode. And it handles a lot of protocols, which, like I2C, SPI, UART. And so, for example, here in the screenshot, you can see that we have a I2C signal, and we decode it using the I2C decoders on the fly. And all of this is done with libsigrok decode. Also, there's the Scopy scripting environment. So Qt provides a JavaScript shell that allows the application to be scripted using JavaScript. We implemented an API to set and run the instruments, to use measurements, to use raw values from buffers to analyze them. And we actually use this scripting environment in our factory to do automated tests for the boards. However, there's a downside to this. Scopy still has to run in order to automate the instruments, so that's not as good. When we created Scopy, we we had like a modular approach in mind. So developers can create their own instruments. There is the tool launcher class, which provides the container for all of the instruments. The tool class provides a base for all of the instruments, and the I/O context is provided by Scopy. And there's an example if you're into, hacking or that kind of thing. There's an example on our repository on how to do a dummy instrument. We also created, so like I said in the previous slide, that a downside of the Scopy scripting environment is that you need Scopy to run. We created libm2k, which libm2k is a C++ library which makes interfacing with M2K easier. You don't have to run Scopy. It's just a C++ library. You write your program, you link against it, and you don't need anything else to interface with the M2K. We also created Python bindings for it, and there's a small example there on how to read the analog voltage from the ADC. As you can see, it's just like 6 lines of code. It's super easy. So in conclusion, what we liked about GNURadio was that we could easily modify the signal chain, modify the signal acquisition. It took very few lines of code. We only needed to change very few lines of code in order to change like major features in the instrument. And the GNURadio provides lots of blocks that can be used right out of the box, and you don't have to care about the implementation details. What we didn't like about GNURadio was that there was no easy way to do flow reconfiguration, and we kind of needed that in order to multiplex the instruments. And it was not that good for trigger operation, and especially for single shot acquisitions. But for streaming, it worked very well for us. So in the future, we also intend on adding support to multiple I/O devices, such as the Pluto SDR. And we want to add better plugin support, so you don't need to recompile everything. Just make use of the JavaScript, or maybe just make your own DLL, but you don't need to recompile Scopy altogether to have your instrument inside our application. Thanks.
5-6 minutes questions.
What are the differences between the Pluto and the ADALM 2K?
So
it's just the connector?
Sorry?
It is just the connectivity?
So the ADALM 2000 is a baseband device. You just use it to do analog measurements without I and Q. There's no LO on it. It's not radio. It's just analog measurements. And yeah, there's on the analog side of things, you have multiple options, but there's also the digital front end. Does that answer your question?
Yes. And for the price, is it about the same?
Yeah, it's also $100, yeah.
You said you were sampling at 100 megasample per second? And so can you stream all of the samples?
No, we can't stream all of the samples at 100 megasamples per second. We do buffered acquisition. We get data at 100 megasamples per second, and because we have Linux running, I mean, we have the capability to get like a lot of data, but we can't stream data at 100 megasamples per second. But that's also because of the USB connectivity. USB can't handle that amount of throughput.
What about the PGA part? Do you have a space to program your own code? Is something similar to Pluto SDR?
Yeah.
It's identical. So you have two DMAs, I guess, no, to transfer and to receive?
Yeah.
Also, the rest is empty space to your own code. The PGA also have two DMAs, have interpolation, decimation.
Yeah.
Also?
Yeah. I mean, it's a little different because the chip is different, but it's basically the same principle.
It's not the same chip?
It's not the same chip. So we use the AD9963 chip, which is kind of an instrumentation chip. But for the Pluto, we use the AD9363, which is an SDR.
So I guess the FPGA is the same FPGA.
The same FPGA.
Okay. Okay.
Thank you for the presentation. One question about the hardware. When you do single-shot acquisitions, what's the buffer size? How many samples can you measure?
It's quite big. It's kind of so for Scopy, it's 8,000 samples. But with libm2k, you can go way past that. It's just that you won't use this UI, but you can go way past that. I think it's in the tens of 1 million samples.
Thank you.
One more question? So let's move ahead. Thanks, Adrian, again.
Thank you.
Thanks a lot. Next up is embedded connected receiver system for nanosatellites here. Talk is given by François, yes?
Okay, thank you. My name is François Spies, and I am going to present you a subject about embedded and connected receiver system for nanosatellites in low Earth orbit. So the presentation will start with satellite signal reception, then a form of deployment on mesh on Earth for ground station, and then I follow with the hardware and the software of the ground receiver, and how we are going to manage the Doppler effect on the signals. And I will finish with the functions to decode the signal. So first of all, why do we have nanosatellites on space? Because there is scientific and academic applications. There is also image processing application. And recently, we have more and more application about Internet of Things for isolated objects on Earth, like containers, small chips, sensors in desert land, wild animals monitoring, etc. And some projects are growing currently. So in the year 2K to 2012, there is something like less than 20 nanosatellites per year which are launched. And in the near future, it will be something like 500 to 1,000 a year. So what is our objectives on this ground receiver? We want to build a low energy and low cost ground receiver for LEO satellites. We want to use, of course, fast functions, mainly integer functions, to decode the received signals. But we need to take into account the Doppler effect. And we are going to avoid using filter functions in order to save energy and time. So the altitude of this satellite is around 400 to 600 kilometers. It takes something like 80 minutes for each orbit, and the speed is about 7.5 kilometers per second. And the coverage on the ground is around 5,000 kilometers. So usually the passes of the satellites is over North and South Pole, like on the graph. And there is an application. This is a view of a JPredict application, which deliver some information about LEO satellites on their passes. And on red here, you can see the coverage of the satellite. So what is inside the satellite? So usually you have communication on amateur radio frequencies, such as VHF or UHF, but also S-band. The transmit power is usually around something like half watt. And the modulation is mainly BPSK or GMSK, but there is also FSK, ASK. So the speed is quite low, between 100 and 10 kilobytes per second. And the Doppler effect is something like roughly 10 kilohertz for 400 megahertz. And the receiving power depends on the position of the satellite compared to the ground station. So on zenith altitude, it will be something like 500 kilometers and minus 110 dBm. And for the satellite in horizon altitude, which means something like 2,500 kilometers, it will be minus 120. So this is the ground segment if you want to have 3,500 kilometers, but it's an optimistic view because SatNode.js, as you see, is a realistic deployment, and it's not as well covered as this picture because we have nothing. It's just a way to have a good coverage on Earth. So if you have something like 80 ground station well placed in the world, mainly using eduroam Wi-Fi connection, because you know that internet access is something which can be difficult in many countries. But when you have a university using eduroam Wi-Fi connection, you can use this internet access. So what about the hardware components? We use three types of hardware. One which is powerful, which is a classic computer with an operating system using SDR USRP B200. And we use GNURadio or GQRX. And here we use also Raspberry Pi 0 with Linux operating system, and the USRP B200 or the Pluto SDR, like in the previous presentation. And finally, we also use a microcontroller without any USB port, and we use, in fact, an SDR IP, which means the SDR is on another device, and then thanks to the Wi-Fi connection, the microcontroller can receive the baseband signal. So for the software, we use JPredict, as I said, for satellite passes and also for Doppler correction. There is an option to do that. GQRX for converting the signal in baseband, and also GNURadio to use and develop basic function, and also to generate a set of signal in order to test our function. And finally, we use also the IDE Arduino to develop our microcode on the ESP, on the microcontroller, ESP8266. So this is a step to decode the signal from LEO satellites. So first we need to detect a carrier near from the frequency, something like 10 kilohertz of accuracy. Then we need to synchronize the local clock with the received signal, something like more or less 300 hertz, in order to lock the synchronization. And then we can detect BPSK signal in the synchronized signal. And finally, we construct the data using serial function in serial. So this is frequency variation due to Doppler effect. So first of all, when the satellite is near from the horizon, you are going to have a high Doppler effect, but with a low variation. And then when the satellite is on the zenith, you are going to have a low Doppler effect, but you are going to have a high variation, something like 80 hertz per second. So in order to understand the Doppler effect, this is a small example without the Doppler effect. So you have a BPSK signal times a carrier, and then you send it, and your signal is centered on the frequency choose. Then you have the Doppler effect, same things as the previous scheme, and then you are going to observe Doppler effect of something like 10 kilohertz, for example. And on the receiver, you are going to receive the signal times the carrier, and then you are going to receive the baseband signal, which is shift from the zero frequency. So finally, you are going to have to receive on the baseband a signal which is composed of the signal and the Doppler shift. The Doppler shift will be like an envelope with a low frequency, and the BPSK signal, which will be the high frequency, something like that. Something like that. These are the envelopes. So the first task, is to recover the carrier at something like 10 kilohertz. So you have 2 or 3 options. So first you can use gpredict, which deliver a calculated Doppler shift based on non-satellite passes on the speed. But this information must be very accurate in order to have the right frequency. Transmitted signals are not always known and included in the satellite characteristics, so you need to add it in gpredict if you don't have this information. And sometimes there is a lack of accuracy on the satellite passes. So you need to take this into account because you are not going to correct the carrier properly. So it can be used to activate the carrier recovery on predictive window time. This is a good point. Like this, you can receive at the right time according to the window. So if you don't use gpredict, you can use an existing carrier recovery with low consumption, but FFT can be out of this scope. So we are going to think about carrier recovery with low consumption, but it's still a job to do. And if there is many ground stations, the information about the accuracy of the path can be exchanged between the ground station in order to have always a known Doppler shift. So what is the problem with unsynchronized signals? So when you have a nearly perfect data signal, you are going to see something very nice like these curves. But on a realistic data signal based on BPSK, or for example, with an additional low frequency, you are going to receive something like that. And it's quite difficult to read the data on such curves. So our idea is doing a transformation without using a filter function. So we measure the maximum amplitude on the signals, on the variation of the maximum amplitude over time. And when we see that here is the maximum amplitude, on the next one, on the next envelope is at t plus delta t, and so on, we can define the low frequency, and then with this information, we can correct the signal. And to correct the signal, we use our piece of software on GNURadio, and we output the results, the baseband signal, and we have an external program which calculates the maximum amplitude as on the previous slide. And then when we calculate the low frequency correction, we can send it back to GNURadio in order to take this information into account in order to have a correct baseband information. And this is our loop, which is a software loop. So when we have all this information correctly, we can decode the data, and then using GNURadio or a dedicated piece of software, we can do the serial tasks in order to get the correct information. So what are our results? Our results is the synchronization on the received signal works on GNURadio and on our dedicated source code on computer or on Raspberry Pi. So test has been conducted on simulated signals using constant Doppler shift up to 500 Hertz, but we need to go further with Doppler effect with variation. So the demodulation and decoding of received data works on well-formed signals, but is not working currently on minus 110 dBm, but we are working on it. On the demodulation of data received on the microcontroller works, on signal can be sent by internet in a wave format or other things. So what are the conclusions? The conclusion is we had great experiences because, in fact, we are working a computer scientist on the electronics, and it's really interesting because of this piece of software. SDR is something like halfway between electronic and computer science. So we are looking on developing function which comes from a numeric world, but we are trying to avoid filtering when it's possible, of course. So we need to improve the demodulator function to very low signals in order to have realistic signals. Then we have to develop also the numeric carrier detection function for low power microcontroller. And probably we can add something in the set of ground station already, which are already existing, which are SAT-Node.js, as we see previously. Thank you for listening.
That's right. Are you using the ESP for the receiver in this project? I wasn't quite sure.
To compute the data, the ESP is not for the high frequency part, of course. It's only for the functions after the reception. Here is SDR connected to a real PC, and then we receive the baseband signal on the SP. Here it's ESP in the center, but there is bad contrast.
What is the lifespan of a nanosatellite? Does it fall quickly, or how long does it live?
It's something like 1 month to a few years. Is it the right question? Yeah. Sometimes this type of nanosatellites are working for a very short time because there is a bug in the embedded code on the It depends of the altitude, but if on such altitude, probably it will fall in the next years. But on nanosatellites, usually there is no guiding. There is they are flying on their own. There is no motors, and not any motors, not any gas to control.
I'm going to talk about KiwiSDRs and some interesting work which is being done on them. As you can see here on the lower left side, right now there are around 400 of these receivers online. They are publicly accessible, and they are quite widely geographically distributed. Of course, there are some holes, but there's a large concentration in Europe and in the US, and also some in Asia. Okay, on the right-hand side, you see this KiwiSDR. It's an add-on board to a BeagleBone single-board computer, and I will talk later more about it. Now, that's about myself. I have a background in theoretical physics. And then I worked for a few years at a German aerospace center in Neustrelitz with GNSS, and in particular on the impact of the ionosphere on GNSS performance. So on the right-hand side, you see a global map of so-called total electron content. This is proportional to the error you get on a link to a GPS satellite. And this is one of the things I developed there. And now I'm based in Krakow in Poland, and I'm part of one of the four big experiments at CERN, at LHC. So first I'll talk about the KiwiSDR itself, the system architecture, the web interface. There's a command line interface, and then now there's also this GNURadio source block. And then I will cover some applications of that. One is the coherent combination of IQ streams, and then talk about decoding of digital HF modes. And then I will quickly mention time difference of arrival, geolocation. So as I already mentioned, the KiwiSDR is an add-on board, so-called CAPE for the BeagleBone Black single-board computer. It was developed by John Simmons, and it's open source and open hardware. You can check out the source, the source code and also the PCB. It's based on a web interface called OpenWebRx, and also it's based on a so-called GNSS receiver by Andrew Holm. But I think it's fair to say that by now it has surpassed, it's based on them, but it has surpassed them quite a lot. So this is the system architecture. The frequency range is from 10 kilohertz to 30 megahertz, so that covers VLF to shortwave. It has an ADC which runs at 65 megahertz and has 14 bits. And then also it has a part related to GPS reception. It has the Skyworks GPS front end, which delivers 2-bit samples at 16 megahertz. And then it uses this Xilinx RTX 7 FPGA. Then all communication with the receiver is done through this open source web server, which delivers HTML5 WebSocket streams. And then there's, of course, lots of client-side JavaScript. There are 3 software selectable configurations. You can have either 4 channels sampled at 12 kilohertz, 8 channels sampled at 12 kilohertz, or 3 channels sampled at 20.25 kilohertz. So that's limited by the processing power and the throughput of the FPGA and the BeagleBone. Okay, this is how the web interface looks like. So you can see this waterfall diagram. This you see in your browser, in a web browser, in any web browser. You can select out of the spectrum either 12 kilohertz or 20.25 kilohertz audio samples. You can demodulate them in various modes. There are up to 8 users depending on the configuration, and there are quite a lot of extensions. So you can do fax demodulation, slow scan TV, CV, FSK, and so on. And here you see one of these extensions which allows you to get information about digitally modulated signals. Here you see an 8 PSK constellation diagram. So there's a PLL locking on the carrier. And this is a certain kind of quite common signal called Steinach 4285. And this strong PSK component is the sync pattern. Now, as I mentioned, the KiwiSDR has this Skyworks GPS front end, which provides 2-bit samples of the GPS L1 band at 16 megahertz. Out of these 2 bits, 1 bits are currently only used. And then the processing is split between FPGA and the BeagleBone. So the Doppler and CA code offset are computed on the BeagleBone using a snapshot of samples. Then the tracking loop updates are done on the FPGA, but are using a so-called eCPU. So that's not fixed by a Verilog, but you can run programs on that on a very simple CPU. And the demodulation is done on the FPGA in Verilog. Then initially this worked only with GPS L1 and CA code, but then it was generalized to this QCSS satellites. It's a quasi-Venus satellite system. It's mainly used for Japan, and it's interoperable with GPS. And then also recently to Galileo E1A. There the tracking is in principle more complicated because of these binary offset carrier signals, but it turned out to work in the end. And then position solutions are based on so-called snapshots, and a snapshot is the current state of all tracking loops. And what's interesting, it includes a 48-bit counter, which is aligned with the ADC clock. So if one does a position solution on one of these snapshots, one knows the absolute time of the ADC clock for that sample. And in this way, one can time align samples from different KiwiSDRs. So now almost each of these 400 KiwiSDRs has GNSS enabled, so you can combine streams and do all kinds of interesting things. Then one thing I developed was this extended Kalman filter position solution. So of course you can do this position solution in a single shot, and then this is done every few seconds, then you forget where you are and start new. But it's better to use this so-called extended Kalman filter because you can remove outliers, and also if there are less than 4 satellites available, you can still have a time information. So this is the state, you have X, Y, Z in time, and also this clock correction, this T dot. Here I use natural units, always either in meters or relative to speed of light. And then the update is, these receivers, they don't move, so they stay at the same place. The time is the last time plus delta T. And the clock correction also is assumed to be constant. And then you feed all this into this extended Kalman filter. And here on the right side, you see delta X, delta Y, delta Z. And the blue points are the single point solution, and the red points are the extended Kalman filter solutions. So it's no surprise that it's very much smoothed. And this on the top right is this clock corrections, this CT dot, which can vary quite a lot because the local oscillator is not temperature controlled. So there are quite large temperature changes. Okay, this is in this so-called admin interface. You see this sky plot of all currently visible satellites. This is a location where the view of the sky is limited by some buildings, so you see just one half of the sky. But you see a number of satellites there. This Q194 is from QCSS. There are a few Galileo satellites, and the rest are GPS satellites. And for all of them, you get the status of the tracking loops, if the ephemeris data is present or not, azimuth elevation, and this strength, signal strength. Okay, that was the web interface and the position solutions. Now there's also command line-like interface, and it's done in Python. It's called KiwiRecorder.py. It's based on work by Dmitry Yanukovych. There are Python 2 or 3 WebSocket clients which connect to these WebSocket streams, and you can get either IQ or other mode samples into WAV files. Now for these time tags are available only for the IQ mode, and there's a custom wave chunk which contains the GNSS time. So you have this custom wave chunk with the time and then the samples, and then again. And use cases are whisper monitoring, if anyone is interested in this. KiwiSDRs are among the top ranking stations in whisper monitoring, and also this time difference of arrival techniques. On the right-hand side, you see the help of this KiwiRecorder.py. So it has evolved over time, and there are many options, like doing timed recordings, having a squelch, only record if there's a signal above a threshold, and so on. Okay, then this is the KiwiSDR GNURadio source. It's an out-of-tree module. You can check out the code. And it connects to this WebSocket server and obtains from there samples. And this is done using this BoostBeast library for the WebSocket part. For now, it contains only IQ mode. And these timestamps are converted into RX time tags. And then there's an analog part for recorded WAV files, which have this custom WAV chunk. And again, the timestamps are available as a stream tag. So in one caveat, because of this boost beast, the recent boost version is needed. But I know of several successful installations with standard GNURadio 3.7 versions. Okay, now I come to the first application, and that's the coherent combination of IQ streams. As you see, the bandwidth is quite limited. You can get out of this. So one idea is to take 2 streams, each with 12 kilohertz, and combine them to one with 24 kilohertz, if they're just adjacent. So for this one, can use these time tags, because everything is based on the same ADC clock. They are samples from the same KiwiSDR. And then there's this polyphase synthesizer in GNURadio. This is used in 2x oversampling mode. And then the small complication is that you need to align the phases. So the center frequencies of the signals you record, they are accurate to GPS precision. But the sampling frequency itself is subject to this temperature drift and has several tens to 100 ppm offset. So if you look what happens if you have one stream at a frequency f0 minus delta f and one stream at f0, and then go either the half down or up from the other, then you get this phase offset. And there's a part linear interface and there's a constant offset. So the part linear of the phase you can convince yourself is given by this. And then once you subtract this, you still have to align the absolute phase. Then one can see how well this works. And this is one example using a digital radio mondial signal on shortwave. So there are 2 inputs. One stream number 0 is recorded at f0 minus 7.5 kilohertz. The other at f0 plus 7.5 kilohertz. Here, top left and top right are the spectra of each of them. So this is the signal. And then the bottom you see the combined one, the combined spectrum. And on the bottom left, you see this phase QA plot, which is the relative phase of these 2 streams where they overlap. And this should be constant. If this is not constant, something is wrong. So these are the power spectra themselves. Here you see the waterfall diagrams. It looks all smooth. You see this propagation effects of shortwave, this selective fading. And then the last check is to run this through a decoder and compare the quality of this combined stream with the recording made in parallel on the center frequency. And if you look at this dream decoder output, so both are successfully decoded. And if you look at the SNR, it's very similar. It's within fluctuations. So. Of course, this is kind of academic example because in the end you want to use it to record wideband HF signals. Of course, the bandwidth of this is not needed for the digital radio mondial, which has I think 10 kilohertz bandwidth. But I've used it for wider bandwidth to get interesting information. So that's the coherent combination of IQ streams. And now we'll talk about how to decode digital HF modes. So this is also a GNURadio out of 3 module. Somehow I forgot to put the URL for it. So I consider a family of digital modes, mostly military ones, and all of these can be characterized by having a preamble and then a frame structure given by known and unknown symbols. And this is different for each mode, and there are quite a lot of variations, what is in the preamble, so on. But then all of these on HF need a Doppler offset correction, and then need to have an adaptive filter to track the state of the ionosphere, how it's reflected in the selective fading. And the idea is to have a generic decoder where these 2 things are separated, so the adaptive channel filter and the Doppler offset correction is done in C++, and all the rest is done in the Python module loaded in block.start. So this is this adaptive LMS decision feedback equalizer due to Wiedro and Hoff. That's quite old. It goes back to the 60s, and it's based on earlier work by Wiener in the 40s and 50s. What is interesting is that this is a very early ancestor of today's neural networks, and this it developed gradually into neural networks later on then. So this is one example. So you have filter tabs, you have NB backward filter tabs and NF forward filter tabs. So here is now. You have the past, and if you look at the past and the future, and then you kind of adjust these filter tabs such that you get the wanted response for the known symbols. There's also a part which feeds back the decisions themselves. It's in general not so important, but anyway, I implemented it. One thing you need to take care of is that you need to recenter the filter tabs because the clocks are usually not aligned between transmitter and receiver. And here, this just to mention that there's an interesting other GNURadio out-of-tree module which has lots of different filters, but for example, it lacks this recentering of filter tabs as far as I know. Okay, one small point is that for the unknown scrambled symbols, if it's, for example, BPSK scrambled to 8PSK, which is quite common, what you can do is to unscramble, make a hard decision on the BPSK, and then re-scramble again. This helps quite a lot. This is a very high-level overview of the GR-digital HF. So you have this root raised cosine filter, which is needed for almost all modes. Then I use this digital CoreST block to correlate the preamble. Then there's a block doing the Doppler correction. And then this hides all the complexity of dealing with the protocol and the physical layer. And then it outputs the descrambled symbols and the decoded bits. And the idea is to kind of abstract what is common between all these modes. So each mode has a function called getPreamble. The constellations are defined in Python and then transferred to GNURadio as NumPy arrays with this D type. So you have the points, which are complex numbers, and symbols, which encode the coding for the points. And then the adaptive filter just needs to know how many symbols are next, and if they are known or unknown in this scrambling. And this is encoded in this NumPy type. So you have the symbols, and then the scrambling if there's something, and there's also this scramble used for X or used for QAM modulations. Anyway, it's a small detail. And then it does some processing, and then the Python part returns a status whether to continue or not with the processing. So this is one example. This is this well-known Stanek 4285 mode. These are the descrambled symbols. So this is the structure of this mode. It has a sync pattern, and then it has a sequence of unknown symbols and known symbols. And what you see here is the phase of the descrambled symbols. So this is sync pattern. Then you have the data, and there you have the known symbols. They are descrambled to have just 0 phase. Yeah, and there in GR-digital HF there are examples also for other modes. And you could, if you would do a demonstration, you could now also look at the soft decisions, the adaptive filter tabs. Then these are some constellations I observed on H, which are being used on HF and processed through GR-digital HF. So this is one nice QPSK with a very high signal-to-noise ratio, this 8PSK. And also these QAM modes, which on HF are kind of more aesthetic than in other modes, right? And of course, for this you need this adaptive filter because the ionosphere deforms it to, if you do it just naively, there's no chance to get this kind of displays. Okay, this is a summary on this digital mode. So it's work in progress. There's still lots of debug output. It might or might not work out of the box. The supported digital modes are using phase or QAM modulation. It does not work, for example, for OFDM modulation. And the form of the physical layer protocol should be compatible with having a preamble and then a sequence of known and unknown symbols. So that includes quite a lot of modes, and some of them are implemented already, including some extensions or variations of this 110C mode. Because this way of doing it makes it easy to explore maybe unknown signals or different variations of modes. Then there's no demonstration because of some computer issues. And then I just want to And I just want to quickly mention this TDOA geolocation. I'm not sure how I'm on the time. I have. Okay. So as you have seen, all these KiwiSDRs, if the GPS is enabled, they have these accurate timestamps, and one can use this to look at the cross correlation between two KiwiSDRs for the same signal. So what you get here are cross correlation peaks and their error, because if you do it in time, then you will see some spread in these peaks, and this can be used to generate TDOA maps. So for the maps, each point on the grid is assigned kind of a chi-square value, which indicates how much is compatible with this given grid point being the most likely position. Here's the Octave code if you're interested. And John Simmons has integrated this into a KiwiSDR extension, so now everyone can run it on any KiwiSDR. And it's using 30-second long recordings. The GNU Octave code, and also the Kiwi recorder is running on a central server. And then what you get out is TDOA maps, where you can see the most likely position. I have to mention that at this moment there are no correction for ionospheric propagation effects. So in general, one would expect it not to work particularly well on HF, but since one uses these differences of propagation delays, they quite often cancel. So actually it works surprisingly well. This is one example. So it's using 3 KiwiSDRs, one in Brazil, one in the Dominican Republic, and one more up, not shown here, in Florida. And the signal is slightly above 17 megahertz. It's a digital signal, and it's a known signal. And this is what you get from the TDOA. So these are likely positions, and because of the way the KiwiSDRs are spaced, it has kind of an ambiguity, but this one matches the known signal, which is a French naval station, FUE. Okay, I would have more examples, but I thought I would focus more on this digital HF modes. Okay, but maybe I'll show 2 more slides from the appendix. So here are the cross correlations. This is on VLF. This is this well-known DCF77 signal. So cross correlations between 3 stations in Europe, KiwiSDRs. Actually, these are the very first plots I made. And the red dot is the peak of the cross correlation function. So from each of these combinations, you get the mean of the red dots and the standard deviation. That's the input. And then to make the maps, so for each pairs with known position xi and xy, you compute this sigma square, which is the great circle distance between your point and the receivers, minus the delta t squared over sigma squared of the measurement. So if your given position is compatible with this measurement, then this is 0, and otherwise it blows up. And then having a number of pairs of this measurement, you form this chi-square. So, and then the most likely position is the position where this chi-square has its minimum. The fancier way of writing is this argmin, but it's again the assumption that the propagation is at speed of light at ground level along the great circle path. Okay, so now this brings me to a summary and outlook. So this KiwiSDR is a new source block for GNURadio. I covered the coherent combination of IQ streams. Of course, the next step is to coherently combine streams from different KiwiSDRs. This was for a combination from the same KiwiSDR. Then this GR Digital HF is an attempt to make decoding digital HF modes easy. Also to make it possible to do it rapidly for new modes. Then this TDOA geolocation can work surprisingly well on HF. And I would like to stress that KiwiSDR is open source and open hardware, and any contributions are very much welcome. And also, it should be obvious that there are many more applications possible, and there are more and more receivers being added to the network. Okay, that's everything, so thank you.
Hey, some questions, okay? Paul.
Thanks for a very, very interesting talk. I remember KiwiSDR was a Kickstarter or something like that.
Yes.
Are they still available?
Yes, they're still available.
Okay, thank
they're
you.
still being produced by Seed Studio in China. But they're in stock basically all around the world.
Thank you. This is very interesting. I was actually wondering, you built this as a cape for the BeagleBone, right? Yes. Is it possible to interface this with any other single board computer? I mean, is the interface like open and easy? I think it would maybe ease a little bit the adherence, because, I mean, like, for example, if you use a Raspberry Pi, which is much less expensive and much well known, maybe it could be interesting.
Yes. Well, the reason that this BeagleBone is used is that at the time it was being developed, the BeagleBones had more computing power than Raspberries. Now it's the other way around. I'm not sure how easy it would be to adapt it to a Raspberry Pi. I mean, I don't think the pins would match even for the cape. Yeah. Might be something to look at, yeah.
Yeah.
Can you give us an idea about this synchronization accuracy you can achieve if, for example, given you have 100 kilometers distance between the two receivers, what time offset accuracy you expect that can be achieved by this method of synchronization?
Okay. Well, the accuracy of the timestamps is GPS, or GPS plus Galileo accuracy, which is tens of nanoseconds. That's of the timestamps itself. Then you need to know the location of the KiwiSDR quite precisely, and I think those are set by the users, so they might be off if the user doesn't set it correctly, and also I think they are truncated to 2 digits in degrees, not to reveal the user position or to get into problems. So there's already, I think, a few kilometers, up to a few kilometers error just by the positions. Then, so the relative accuracy of the timestamps themselves is tens of nanoseconds. The absolute accuracy drops out because you take differences if you assume it's the same for each KiwiSDR. But I checked on DCF77 the absolute accuracy, and it's better than, I would say, 20 microseconds. But this is more due to the fact that the DCF77 signal is just not very fast. So. And then in terms of the most likely position on very long, on VLF, it's a few kilometers. If you do it, for example, on this low run signal 100 kilohertz, which is ideal because it has ideal cross-correlation properties, you're within a few kilometers. And on HF, it's tens of kilometers, I would say, typically, if it works. Unfortunately, there are no systematic studies of this accuracy. It would be very interesting to run it continuously and see what's going on.
Can you get, have you received a low-run signal from Germany? I'm struggling to get one, the Anton emitter, the low-run signal.
Oh, it worked a few weeks ago. It's not?
How much? WebSDR. On the WebSDR, I see that it's emitting, but all the way from the Lausanne, so it's about it's about 1,000 kilometers at 100 kilohertz. We cannot fetch a
Well, it depends on your local noise. I don't know how big your noise and what kind of antenna you're using.
You get it from, you get the right signal.
It depends where, but I can use several KiwiSDRs and...
No more questions? So let's thanks again. So Antoine Blais from ENAC will present us using GNURadio companion to improve student understanding of signal processing theory through VHF omnidirectional range signal demodulation. Oof.
Thank you, Mr. Chairman. Yes, this is a very long title. Thank you. But it's a very long title. So I'm Antoine Blais, and I will present this work which was done with my colleague, Christophe Morlas. So please let me introduce the subject. So as teachers, we have, from our experience, we have seen that the complex notions which are being taught during the signal theory and the signal processing courses, well, they need to find some practical realization for the student to clearly understand what they are. So often we give some practicals to focus on specific points. However, there was also a need for a larger project to make the student understanding why these courses are in their timetable. So this was done using a long project form, which gives time to the students to build by themselves a VOR receiver. So in fact, we give the students a DVB-T USB dongle, one dongle per pair of students, and we ask them to produce a VOR receiver using the GNURadio companion software. So please note that the learning of GRC is not the main purpose of this project. What is interesting for us is the signal theory point of view. Okay? GNURadio is an interesting aside. However, it's not the main goal of this project. It's a wonderful software. That's why we use it. However, we want to focus on signal theory and signal processing. So this presentation provides insight into this long project. Here is the outline of my presentation. First of all, I'm going to present a model of the VOR signal to clearly understand what we are going to process as a signal. Then I will focus on what was important for us, that is the pedagogical approach. In a third step, I will detail two interesting technical points the students have to cope with. And finally, of course, I will draw some conclusions. So first, let me give you a model of the VOR signal because we want to establish this as a starting point of the project. So the VOR system is a navigation aid which is designed, as it is written here, to give the angle in relation to the magnetic north to the aircraft from a ground radio station of a known position. In this way, the pilot can navigate towards the beacon or from it. To transmit this angle, the VOR beacon simultaneously transmits two 30 Hz signal components, one with a constant phase, whatever the direction in which it is received, and the second one with a phase which consistently varies according to the direction in which it is received. The onboard receiver, of course, has to measure this phase difference to display it to the pilot so that he knows the angle in which he is navigating. So I have a graphical illustration here from this website. Okay, you can imagine that at the center you have the beacon and your aircraft is in some direction. For example, let me take the 145 direction as an example. You have two 30 Hertz components which are then shifted by this angle when received on board. In this way, the pilot knows that it is in this angle from the beacon. Obviously, the two 30 Hertz components are not transmitted as is because we would need very large size antenna. That is why, in fact, the two 30 Hertz components are transmitted via an hybrid signal which is modulating in amplitude a carrier frequency. So we give the students a time model of the signal. So we give the students this time model of the signal which is transmitted. You can see that it is an amplitude modulation here. M of t is carrying the angle of interest. We have a carrier frequency here with a high frequency term which lies in the VHF band, and more specifically in this range of frequency, 108 to 118 megahertz. Let me detail the hybrid signal now, because it is the one which carries the information. First of all, at the top, we have a first cosine term at 30 Hertz, which carries the QDR. So the QDR is the angle of interest. It is the magnetic bearing from the station to the aircraft. So it is carried by this 30 Hertz component. Then we have a second term, which is carried by a 1020 Hertz carrier, which is the identification of the VOR beacon. Because when the pilot on board selects a specific frequency to select a corresponding VOR beacon, he can make an error. This identification code, which is a Morse code, is here for him to check that he is on the correct beacon. It's for safety reason, of course. Then we have a third term here, which is carried by a 9960 Hertz carrier with a phase term here, which is varying in time. In fact, as we can see in this detailed expression, we can see that it is an integral sum of a time-varying cosine at a frequency of 30 Hertz also. Hence, it is a frequency modulation signals which carries this second 30 Hertz component. What is to be noted here is that this first 30 Hertz component and this second one has the same initial random phase here, because they are from the same oscillator. And then, inside the receiver, if you are able to recover this first cosine and this second one, well, you just have to make the difference between the two arguments here and here to recover the angle of interest, the QDR. It is the job of the receiver to make the difference between these two arguments to recover the QDR and to display it to the pilot. Yes, a short note here to mention that this QDR term, the angle term, can be in this cosine instead of this one. From the receiver point of view, it makes absolutely no difference. It's just a different VOR beacon technology. For the students, this time model is quite complex to handle. And at this point, it is an opportunity for us, the teachers, to show them that when the time description of a signal is too complex, maybe in frequency it's much simpler. And that's why we give them this synthetic representation of the PSD, the spectrum of the baseband for VOR signal. We can clearly see that the different time components, in fact, in the spectral view are distinct, separate. Here we have the line at 0, which is due to the 1 plus m of t. We have the two lines here corresponding to the first 30 Hertz component. We have a line here, which in fact is slowly modulated by the Morse code. And of course, we have the frequency modulation term here around 9,960 Hertz, which embed the second 30 Hertz component. An interesting side of this spectral view is that we can tell the student that the bandwidth of this term is plus and minus 480 Hertz. Then we can focus on the fact that here we can safely limit the bandwidth of this signal to 12 kilohertz. In fact, it is slightly less, but we can have a small amount in excess without any difficulty. Having this model set, we can begin to work on the signal, not only to receive it, but, as we shall see, to build it. And it's time for me to focus maybe on what was the most important, that is the pedagogical approach. In fact, facing this wide project to build a full receiver, the students are completely lost. That's why we have decided to put them very strong guidelines so that they can go safely and quietly to the end of the project, that is a working VOR receiver. Our first step is an interactive implementation of a simple FM radio broadcast receiver. In a second step, we ask the students to produce their own flow diagrams, to first read, then display, and lastly, record to a file the IQ samples which are output by the DVB-T USB dongle. And in a third step, we ask the student to produce an IonQ VOR signal generator. Lastly, they have to develop their own VOR receiver. So, this first step about the FM radio broadcast receiver, well, it serves two main purposes. First purpose is to present the DRT GUI capabilities, as it is a very user-friendly GUI. In one step, they know how to use it. And this is a very interesting point in using GNURadio Companion from the teacher point of view. We don't have to spend a lot of time on this guy. It works naturally. Then the second objective of this step is to prove the students that the software-defined radio concept works. In fact, when they first hear the radio output of the speakers of the computer, it's really astonishing for them. At this point, they had only theoretical courses. This is the first time they understand that, well, signal theory and signal processing, you can do real things with it. And it's a great motivation for the rest of the project for them. So I don't detail this flow diagram. You can see it's rather simple. And in fact, for the fastest of them, it takes 10 minutes to build it. For the slowest, let's say 20 minutes. Okay? Oh, sorry. So the second step is on their own to build some flow diagram. The aim here is to give them a more comprehensive handling of GRC and also of the USB DVB-T dongle. They have to produce so their own diagrams, which in turn, first of all, read the samples, display them, and also record them. The recording point is specifically very interesting because we can broadcast one time a VOR signal, they record it, and then they will be able to play it again to test their own receiver. The third step is about their own IonQ VOR signal generator. We provide them with a detailed synoptic view, and they have to build it component after component so that at the end they are able to generate synthetic test signals. This is especially important because not only in this way they understand the VOR signal structure, but also they will be able to test with their own signals their own receiver. Lastly, the VOR receiver. So this is the real aim of the project. Here again, we give them a very detailed view of the receiver to help them build it. As you can see, we have two black boxes here, the FM demodulation box and the phase comparator box. More on this later. At this step, they are fully on their own. They have to build this on their own, and they also have to test it on their own with their own generator. To motivate them a little bit more, we give them this visualization tool, which is a software course deviation indicator, a CDI. In fact, it is a tool with which you are able to see your deviation from the course to the beacon you have selected. With this OPS button, you can select, by rotating the outer ring, you can select the QDR you want. For example, if you want to select, as in my previous example, if you want to select the 135-degree QDR, you do it with this OPS button, and this line here will deviate from the center according to the position of your aircraft from this angle. So it is written in Python, and it is communicating with GRC using a 0MQ socket. It is interesting for the student because it helps them understanding how it works in a real aircraft. Okay? This is not just signal processing. This time it is also inside an aircraft. Of course, as we are in a school, we have some evaluation because we have to give a grade, but it is not the main point of this project, of course, as you have understood it. We have a double point evaluation. First, a 1 hour written examination to check that the main signal processing points have been understood. But from our point of view, the main point, the most interesting part is in the real test, the second point of evaluation. In fact, we have a test of reception of a real VOR signal with a QDR to decode. In fact, the teachers, that is me and my colleague, inside the room, we radiate with a low power a VOR signal using a Marconi 2030 signal generator. The QDR is set randomly by ourselves, and the students have to decode it. That is, in fact, they have to use their own dongle, their own GRC flow diagram, and when they have demodulated the signal, they just have to announce it. Is it correct? It's nice. Obviously, if it's not correct, we don't give them a grade of 0, okay? It's not the aim, okay? We work with them on their problem, okay? The aim is that at the end, they have a working flow diagram which displays the correct value. We want to help them understanding where they made a mistake. At the end, they're happy because they have something which works, and we also are happy because we know that they have understood the signal processing problem. So maybe now I shall focus on 2 interesting technical points. As you have understood, the philosophy of this project is to make students understanding signal processing. That is why we forbid the use of high-level blocks like the FM demodulation blocks, which is available in GNURadio Companion. We force the student to build their own block. And from this point of view, there are 2 blocks which are especially interesting: the frequency demodulation block and the phase comparator block. So, some words about the FM demodulation. This time, also, we give a synoptic view of one demodulation method among others. The students have not only to implement this, but to understand how it works. Because here, as you can see, there is a variable which is unknown, which is a delay. So, as you are not students, I can explain you in detail how we can calculate this delay. Okay? So, S of t is the incoming signal, okay? It is a frequency modulated signal carrying the 30 Hz components of interest. We can multiply this signal by its delayed version. So we have a product of cosine which can be split in a difference of 2 cosine terms. Inside the argument, you have either the difference of the argument or the sum. What is interesting here is that we can see that they are frequency separated. Here, this term in frequency is located around 2 times 9,960 Hertz. This term here is located around the frequency of theta, which maybe you remember is a 30 Hz signal. So in fact, we can delete this term easily with a 30 Hz bandpass filter. That is, at the output of this filter here, we can consider that only the first term here remains. What is more, we tell the students that it could be a good idea if this phase term here could be equal to pi over 2, modulo pi, of course. Then, in this way here, we can convert this cosine term into a sine term. Obviously, there is a trap here. Here, tau should be a multiple of the sampling period. And it happens that you cannot find exactly pi over 2. And, well, it asks questions to the students. You know they are used to math with the exactness of math. And here we think that it is a first step toward their future work of engineer. They have to, well, cope with reality. And in fact, here, they have to accept that this is just approximately true. When it's done, there is a second step. Here, we have a difference of 2 terms at 30 Hz. We suggest them that it would be good to linearize the sign. It is possible if this difference is quite small. For this, you have to set tau which is much less than a period of the 30 Hz. Then, at this condition, you can linearize the sign. Obviously, this time again is just an approximation, so it's not exact math, and it's also a difficult point to accept. But as at the end it works, well, it is accepted. Then again, here, in this time difference, we can identify something which is proportional to the first derivative of this angle. And remember, as it is a frequency modulation, this phase derivative is the information we are looking for. So at the end of this FM demodulation blocks, we have what we expected, that is the first derivative of the phase. The second interesting block is a phase comparator. Well, I think I will be out of time, so maybe I'm going to go fast on this and more. It's okay? 7 minutes? So, okay, let me detail this a little bit. So this phase comparator is needed to extract the phase of interest. Remember, we have to make the difference between the 2 cosine arguments. One is from the baseband component at 30 Hz, and the second one is at the output of the FM demodulation block. It is an opportunity to introduce the students with the ear block concept, so that at the end, their software receiver is not just a huge amount of individual blocks. The students are asked, it is mandatory, to embed their phase comparator into an ear block. We have here a possible implementation of this phase comparator block. This is not given to the student this time. We go a little bit farther in the signal processing autonomy. They have to design their own phase comparator. Here I give also the corresponding flow diagrams. They have to build one by their own. What is interesting here is that this ear block, they are asked to develop it independently from their main diagram, and they also have to test it with an independent flow diagram. We think that it is a good practice for a big development to process in this way. So, some detail of the calculations for those who are interested in. We have 230 Hz signal at the input of this phase comparator block, and what we want is to recover the phase difference. So, first step, we produced a delayed version of the first input. In this way, we are able to produce here a phase shift. Now, if this phase shift is exactly equal to 1/4 times the carrier frequency at 30 Hz, then in fact, we have a phase shift of pi/2 here, which enables us to convert this cosine into a sine. This is useful in the two cross products we are going to produce in a second step. Here, we have a cosine multiplied by a cosine and a sine multiplied by a cosine. More on this later. At this point, please note that the two cross product components here have the same amplitude, whatever the input amplitude of the two signals. They can be different, there is no problem. I have developed here the product of the cosine and the sine. What you can see is that we have our two terms of interest here, a cosine of the phase difference and a sine of the phase difference. We just have to discard these two terms here. We can remark that these two terms in frequency are located around 2 times Fc, that is 60 Hz. We want here to select this time, which is time constant. So, with low-pass filters, we can suppress these two terms. And after filtering, it remains only this cosine term and this sine term. We can just input them into an Artan2 function. In GNURadio, it is called complex to arc block. And then at the output, we have recovered our phase difference, which was the objective of this VOR receiver. It's time to draw some conclusions. What I can say is that it is the third year this long project is given. So now we have reached the stable part of the curve, and we are able to see the result of this project. What we can say is that it is clearly, this project has clearly reached its initial objective, which was to give a larger understanding of signal theory and signal processing to the students. We can see that their knowledge and their skill are greatly improved using this kind of project. And that's all for my presentation. Thank you very much for your attention.
Thank you. One or two questions, because now time is done, okay? Yeah. Sorry.
Thank you. One short question before lunch. Why did you convert all the signals to real signals? Why don't you use complex phasor exponentials? The students in the third year should be able to handle complex numbers.
You mean in my flow diagram, maybe?
Yeah. Also in the flow diagram, you have real signals, but the down-converted signal stream is an I and Q data stream.
Yes.
And then we somehow only work with real signals, with cosines and sines. We could also use complex exponentials here.
Oh, yes, okay.
And this would be, let's say, more realistic.
Well, I would say, as it is an amplitude modulation, the real modulating signal is real. So to recover it under the form of a real signal as soon as possible seems natural to us. And
physical signal is real, I mean.
Yes,
so,
physical.
So you can work it out just by using real signals, and that's fine.
Thank you for the presentation. I just wanted to know how long the student had for finalizing the project.
Okay, it is widespread over several months. I think it's 3 or 4 months. They can work on their own as they want. We have regular sessions with them. If they are stuck on a specific problem, we are able then to help them. But it's on a, yes, 3 or 4 months.